Welcome back to the fifth video about capacitive liquid level sensing. In the previous video, we did some digital readouts of our capacity level with the help of an oscillator built around a 74HCT14 Schmitt-trigger inverter. Card here, link in the description. This time we will try to read our capacity without any additional electronics and chips, just using an MCU. Enjoy! Now you might say, why should that work? I mean, we were so concerned about all these parasitic currents and capacitances here in our little oscillator circuit from the last video, and we talked about all these parasitic effects in the last video and the video before that. Card here, link in the description. Why should that work with a microcontroller without the help of an external chip? Well, the 74HCT14 we used last time to build that oscillator, if you remember, had an input leakage current of a typical 0.1 microamps and input capacitance at the input of typically 3 picofarads. And the ATmega 4809 that I have over there on my Arduino Nano Every has an input leakage current of typically 0.05 microamps. So half the leakage current of our 47HCT chip. And its typical I/O pin input capacitance is 3.5 picofarads. So yeah, okay, half a picofarad more than the 47HCT chip. It also has a Schmitt-trigger stage within its input logic. So we already have basically half of our 47HCT14 chip as a single input in our ATmega 4809. By the way, the ATmega 328P, which you find, for example, on Arduino Nano V3, also has a Schmitt-trigger stage here in its input pin logic. And its maximum leakage current at the input pins is 1 microamps, which is again the same as for the SN47HCT14. Though there is no input capacitance defined here in the datasheet for the ATmega 328P, but I guess it's also, a few picofarads to 10 picofarads. So, how about we build an RC oscillator in software with our microcontroller? Robert from the dystopian future here. In this video I will limit myself to the mechanisms available in the standard Arduino environment for implementing those oscillators and why they will function in principle. Accuracy-wise, their performance is questionable. Anyway, we will learn a whole lot. So, again, enjoy. On the breadboard I have my trusty Arduino Nano Every, and at digital pin 21, which can also be used as an analog input, I have connected one lead of my sensor. The other lead of my sensor goes to the ground rail here. And I'm bridging from digital pin 21 to digital pin 20 with my 10 mega ohm resistor. Also connected to digital pin 20 is an oscilloscope probe. Why I don't have an oscilloscope probe connected to digital pin 21, I will explain later. And here's the whole thing as circuit diagram, really easy. So D20 will be an output and will charge via my 10 mega ohm resistor my sensor capacitor, and I will sense via D21 the voltage across my sensor capacitor. And of course I have the probe attached here. Now for the sketch. I have two byte constants here. First, I have my sense pin, measuring the voltage across my sensor. That's digital 21. And I have a drive pin, which I use to charge and discharge my capacitor over the 10 mega ohm resistor. That's pin 20. Then I have, we saw that in the previous code 2 in the last video, a measurement period of 500 milliseconds. And in the setup, I just do a serial begin, wait until serial is ready, and then I define my sense pin as an input and my drive pin as an output. In the loop, I have three variables: a byte drive pin level, which will be used to store the current drive pin level, and an unsigned in cycles, where I just count the cycles of the oscillation, and an unsigned long measurement finish, which I will use in conjunction with millis to have my 500 millisecond measurement period. I initialize cycles as 0 and my drive pin level as low. And then measurement finish is just the current time in millis plus my measurement period in millis. And then I do a digital write to my drive pin with the preset drive pin level. And then I repeat in a loop until measurement finish is greater than millis. Switch depending on the current drive level of the pin. So if my drive level is low, so we are currently discharging, and my digital read of my sense pin gives me also a low, then we should start charging again. Okay, so I increase my cycles, my drive pin level goes to high, and I write that to my drive pin. If we are currently with the drive pin high, that is, we are charging, and my sense pin has also reached high, then we should start discharging our capacitance again. So a drive level will be low, and I do a digital write to my drive pin with the drive pin level low. That's it in the loop. That will go on for 500 milliseconds while counting the cycles we go through in our oscillation. Finally, I will print out the cycles we went through, and I will convert that this time to hertz, and I will convert the measurement period. You remember that graph period is really the linear stuff, into microseconds. And I currently don't print out the milliliters because we haven't calibrated the whole stuff. On the serial monitor, we can see that there's some oscillation going on. And if we look at the oscilloscope, which should be down here, we also see, obviously we have some oscillation with an extreme jitter. And it's also all very, let's say, sensitive. So I'm just touching here, and you can see the frequency is changing enormously. Even putting my hand here, I really need some shielded cables, but we will have to work that with that. Anyway, let's try and do some measurements. Okay, let's say we are at 4.9 kilohertz or something, and we fill up to the 100 milliliter mark. And we're down to 4.1 kilohertz. 4.1 kilohertz. Okay, 200 milliliter. A bit much, doesn't matter. 2.2 kilohertz, 300 milliliter. Spot on. 1.8 kilohertz, 400 milliliters. 1.5 kilohertz and 500 milliliters. 1.4 kilohertz, yeah, 1.4 kilohertz. 1.4 rounded, and 600 milliliters. 1.2 kilohertz. Yeah, aboutish. So like in the last video with the external oscillator, I put the numbers into a little Excel spreadsheet and generated that graph. So the red line here is our frequency between, yeah, a little over 1 kilohertz up to almost 5 kilohertz over our fill level between 0 and 600 milliliters. And yeah, and then we have in green the period here between 200 microseconds and let's say a little over 800 microseconds also over the fill level. And yeah, and here is the least square error linear curve through our period. And yeah, if you compare that to our result with the external oscillator, the internal software oscillator, well, is terrible, Muriel. I can't do an Aussie accent, so I do a German accent. I can do that. The question is, why? Maybe we have a software problem and everything goes too fast for our little microprocessor controller. However, our shortest period in our oscillation was 200 microseconds, and we can execute at 20 megahertz about 4,000 simple one cycle instructions. And yeah, there's not much going on in that loop. So yeah, even if some of that statements use a few dozens, it doesn't explain that atrocity here. Well, we know we have a Schmitt-trigger input. We had a look at that. However, if you look a little bit deeper into the datasheet, you get conflicting information. So here at the I/O pin characteristics of our ATmega 4809, it says input low voltage should be minimum minus 0.2 volts and maximum 0.3 times VDD. So at 5 volts, that's 1.5 volts. And input high voltage should be at least 0.7 times VDD. Again, at 5 volts, that's 3.5 volts. However, if we have a look further down the datasheet into the typical characteristics, we have here a little graph that plots the I/O pin input hysteresis in volts versus the supply voltage VDD. And at 5 volts, it says here approximately, input hysteresis, little bit dependent on the temperature, should be 1.15 volts. But we just saw that the maximum low voltage is 1.5 volt and the minimum high input voltage is 3.5 volts. That's at VDD 5 volts. That's a difference of 2 volts. And then we have here a figure with the I/O pin input threshold voltage in percent of VDD versus VDD. So at 5 volts, we are at approximately 35%. So the low threshold is 1.8 volts. And the high threshold is at 60%, aboutish 3 volts for VDD. Again, in the front of the datasheet, it mentioned 3.5 1.5 volt min here for the high threshold and 1.5 volt for the maximum for the low threshold. And the delta between these two figures is approximately 1.2 volts, and that corresponds to the threshold here. So how the hell do these input pins really behave? To determine that, I've written a really simple sketch. So I have here still my sense pin, digital 21. In the setup, I initialize my serial interface, and the sense pin is still set as an input. And then in the loop, I just print out the value of my, with digital read, the value of my sense pin, and I wait for 100 milliseconds, and then I repeat. On the hardware side of things, I now feed directly a voltage from my lab power supply into that digital pin 21. And now let's see what happens on the serial monitor as I increase the voltage. Now let's see what happens here on the serial monitor as I increase the voltage. So we start at 1 volt and we go 1.1, nothing, 1.2, nothing, 1.3, nothing, 1.4, nothing, 1.5, nothing, 1.6, nothing, 1.7, no, nothing, 1.8, nothing, 1.9, nothing, 2.0, nothing, 2.1, nothing, 2.2, nothing, 2.3, oh, 2.3, we suddenly get a 1. Okay. Okay. And now we can go 2.4, 2.5, 2.6, 2.7, 2.8, 2.9, 3, 1, 2, 4, 5, 3.5 volts. Yeah, let's go up to 4 volts. Okay. And now let's go down again. So 3.9, 3.8, 3.6, now it gets interesting, 3.5, 3.4, 3.3, 3.2, 3.1, 3.0, 2.9, 2.8, 2.7, 2.6, 2.5, 2.4, 2.3, 2.2, 2.1. Okay, at 2.1 volt, we go back to 0. Okay, I have no idea how you should infer these values from what's written in the datasheet. But let's scan through that critical area between 2 volts and 2.4 volts again, but this time in hundredths of a volt, and I won't call out every value. Okay, that was 2.32 volts where we got high. And okay, I don't expect anything to happen. So let's just go to 2.5 and decrease from there again. Oh, 2.08. Okay. Yeah, we can go down to 2 volts again. Interesting. The good news is the inputs are definitely of a Schmitt-trigger type. And in the first measurement series where I increased in 1/10 of a volt steps, we went high at 2.3 volts, and then when we decreased the voltage again, we went low at 2.1 volts. That's a delta or hysteresis of 0.2 volts. And then I measured it in hundreds of volt steps, and the measurement I've shown you, we went high at 2.32 volts in our reading, and then when I decreased the voltage again, we went low in our reading at 2.08 volts. That gives us a hysteresis of 0.24 volts. Now, because that was a little off from these values, or near enough. I repeated that measurement a few times, and the second time I got 2.1 volts and 2.29 volts with a hysteresis of 190 millivolts, and then 2.13 volts and 2.29 volts with a hysteresis of 160 millivolts, and finally 2.11 volts and 2.30 volts with a hysteresis of 190 millivolts again. So it's a Schmitt-trigger, but it's not very well defined, and the hysteresis is very low. Yeah, so looking at that, a stable oscillator with, relying on the Schmitt-trigger inputs is kind of moot. And here's a little rant. Don't get me wrong, this is still good enough to debound some switches with some RC elements, and I've shown that before in another video, card here, link in the description. But it's not suitable for building a stable oscillator. In comparison, our SN74HCT14 we used in the last video to build a hardware RC oscillator has a typical hysteresis, depending on the supply voltage between 0.65 and 0.6 volts, and we measured 0.68 volts. So that's more than 3.5 times a larger hysteresis than the inputs of our ATmega, which also makes things slower and more stable, because that sometimes less than 200 millivolts hysteresis that can be, jumped by just some noise. For example, your 50 hertz hum or 100 hertz hum in the air induced in some cables and conductors that could jump these 200 millivolts. Anyway, what really irks me is that hysteresis of 200 millivolts or whatever millivolts. I was absolutely, and we had a detailed look at it, I was absolutely not able to derive that from the information in the ATmega 4809 datasheet. Either I forgot how to read datasheets, or I made a grave mistake there. I don't know. Please let me know in the comments. But fear not all is lost. So I modified the program a little bit, and let's see. We still have our 2 pins, and I reattached the resistor and our sensor again to the board. We have still our measurement period, and I have 2 new values. Okay, threshold low 256 and threshold high 267. And these are 10-bit ADC values, so they correspond to approximately 1.25 volts for the low threshold and 3.75 volts for the high threshold. And you can already see we will use analog to digital converters. The setup is completely unchanged, okay? And then in the loop I have still the byte drive pin level and the cycles I'm using to count the cycles of our oscillation. And we still have our unsigned long measurement finish. And the initialization is the same, okay? 0, low, measurement finish, and then write my drive pin level to my drive pin. And we go through the same loop. However, within the switch, we do something a little bit different. Instead of doing a digital read, we do an analog read on our sense pin. And if we are currently discharging, so our drive pin is low, and our analog read says we are now below or equal to the threshold low, then we start charging. And yeah, same code. Analog if we are currently charging, and our analog read tells us that the sense pin we are now at or above our threshold high, then we start discharging. Okay, and yeah, the same code, and I think the serial print is all exactly the same. One note of caution: that analog read, that takes about 100 microseconds, okay? So we will hopefully see a much lower frequency of our oscillation, because we need that, because the sampling rate with our analog read without all the code is only about 10 kilohertz. So we should move, hopefully, or we should move, and we will hopefully be around, somewhere below 1 kilohertz with our oscillations, which will be hopefully ensured by our relative large or comparably gigantonormous hysteresis here of 2.5 volts instead of 200 millivolts. Let's have a look at the oscilloscope and the serial monitor. It oscillates. Great. And yeah, the oscilloscope is saying 600 something hertz, and we are measuring 600 something hertz. Perfect. Let's try it one more time. So I'm rounding the frequency again to just 2 digits, and we're currently at 610 hertz MT. And at 100 milliliters we are at 520 hertz. 200 milliliters 430 hertz. 300 milliliters 380 hertz. 400 milliliters 350 hertz. 500 milliliters 340 hertz. And 600 milliliters 320 hertz. Well, you know the drill. I put the numbers into an Excel sheet and plotted a graph here, and yeah, at first look it looks a little bit better than our our little experiment with a digital input, but yeah, only on the first look. If you compare that to our external oscillator, yeah, just seeing the linear curve here, least square error compared to the actual values, you see that thing was unbeatable so far. A little bit frustrating. So, what went wrong this time? I told you while we were going over the code that we are sampling, yeah, a little bit optimistic maybe, but with aboutish 10 kilohertz. Now assume we have a 1 kilohertz oscillation, the black line, with the charge and discharge flanks here. And if I draw it that way, it all looks fine. However, if we miss at that sample point only our upper threshold by a single least significant bit, we will continue charging until the next sample. And the same game for discharging. If we miss, then here our lower threshold again, but just by one least significant bit in the ADC, we will continue discharging until this point. And the difference between the black curve and the red curve is 20%. Okay, given we only had frequencies between about 600 hertz, a little over 600 hertz, and then in the lower range 300 something hertz, but that's still errors in the 10% range on average, assuming we really did sample with 10 kilohertz. Yeah. Well, that's it for today. We learned a lot and achieved only little. I know, I already called it out. Frustrating, but important to see what doesn't work. And before you write in the comments, but the ATmega 4809 also has comparators. That's better. I know. But they are not available directly in the Arduino environment. Maybe at some point we will use the comparator. I already thinking about that. But before I leave you for good, I wanted to just shortly demonstrate you why I haven't connected the second oscilloscope probe here at the output. Not trying to make any shorts, and if I connect that, it stops oscillating. Why? Because now we have a resistive voltage divider, resistor voltage divider between our 10 mega ohm resistor between from the driving pin and the input resistance of the oscilloscope probe, and that prevents our sense pin to even go above our level that we would consider as high, and so it stops oscillating. And if I return the probe, it oscillates away happily. Not very exactly, not very exact, but happily. Okay. Till next time. Bye.